strong acids are going to ionize or hydrolyze completely. So HCl is a strong acid, HNO3 is a strong acid. And normally we think of them as aqueous. So we'll just start off with HCl aqueous. HCl aqueous, there are two ways we can do this. One, we could just dissociate or ionize it into H plus Cl minus. But there's something special about H plus. What's special about H plus is its extreme charge to size ratio. In other words, it's extremely reactive. Why is it so reactive? Why is H plus so reactive? It's so small. It's incredibly small with a positive charge, meaning it's very reactive. Meaning it's so reactive, it reacts with any water molecules around. H plus will immediately attack water molecules. When H plus attacks water molecules, you know what forms? What forms is this, H3O plus. H3O plus is called hydronium. And so, yeah, HCl is a strong electrolyte, so it should dissociate or ionize completely. But when it ionizes completely, it forms H plus. The H plus is just too reactive. And so we could do it in two steps like this. But the likely it's going to immediately react with the water first. So we could leave it like this, but this is not entirely correct. Or we could just go ahead and react it with water immediately, because we know that H plus is going to react with water. And that's going to form hydronium and chloride. And so, as far as accuracy goes, this is more accurate. It's more accurate, but it takes up too much space. And it's more hassle to keep track of. And so what a lot of people will do is they'll just use this, the ionization equation, with the knowledge that H plus itself is a little too reactive, a little too unstable to exist alone. So H plus aqueous does not exist. Instead, hydronium exists, but it's too much hassle writing out hydronium in water all the time. That we like to leave it like this. And so this is ionization or dissociation. Strong acids ionize or dissociate completely. Or this is hydrolysis. Strong acids hydrolyze completely. So they both kind of say the same thing. And the same thing happens for nitric acid. There are two ways I can represent nitric acid. So if I have a beaker, of HCl, this beaker is labeled HCl, and then inside this, am I going to find any HCl molecules? No, no molecules. Instead, I'm going to find H plus ions and chloride ions. Those molecules are going to be broken apart. Now the H plus ions are just that. When I see H plus, I really know that means hydronium, not H plus, because H plus itself is too unstable. Or if I look at it like this, if I have a beaker that's labeled HCl, then I'm going to have hydronium ions and chloride ions present. And so oftentimes we'll leave it like this because this is more shorthand, abbreviated way of writing things, and we like to use abbreviations, so there's less writing we have to do. So the same thing with HNO3. HNO3, there are two ways. It's a strong electrolyte, so it's going to dissociate into ions. So we could say it's going to dissociate into H plus in the nitrate. Leave it like that. Or we could do a hydrolysis. HNO3 hydrolyzes water to form hydronium and nitrate. Most of the time I'm going to use this because it's just less writing. With the knowledge that, you know, H plus is too unstable to exist. So we need to do something else later. Sometimes I'll write it like this, the hydrolysis. Some things don't hydrolyze or ionize completely. Those are the weak acids. So let's take a look at an example, two examples of weak acids here. H2SO4 is not a weak acid. H2SO4 is a strong acid. H2SO4 will ionize completely, but when it ionizes, only one H plus breaks off at a time. So we have two H pluses. If one of those breaks off, then we're left with an HSO4 minus. Okay, this is step one. In the second step, the second H plus breaks off. However, is HSO4 minus one of the 7 common strong acids that you memorized? HSO4 minus is not. H2SO4, this is a strong acid. However, HSO4 minus is a weak acid. And weak acids are weak electrolytes. Weak electrolytes only partially ionize. To show that it only partially ionizes, I'm going to do this. I'm going to write 2 arrows, saying that this is not complete ionization, it's partial ionization. Usually when we have partial ionization, the extent of the ionization is pretty small typically. And so if I have a label that's a beaker that's labeled H2SO4, what do I expect to find in here? Well, I expect to find no H2SO4 molecules. Because H2SO4 is a strong electrolyte, all those molecules will have broken apart into H plus and HSO4 minus. So I expect to find H plus, HSO4 minus in here. These are what we call the major species. But we're also going to see some minor species. The minor species are the partial dissociation of the weak acid HSO4 minus. So if we have a little bit of dissociation in HSO4 minus, we're going to form some sulfate and some H plus. These are going to be the minor species. And so this one is kind of weird because it's a composite. It's a strong acid and a weak acid. And so we get full ionization and partial ionization. The next example is this one here, HC2H3O2. Do you recognize this acid? Acetic acid. Is acetic acid strong or weak? Acetic acid is a weak acid. And therefore, weak acids only partially hydrolyze, partially ionize. So I'm going to write double arrow like this. Draw some H plus and some acetate. So acetic acid is going to dissociate into H plus into acetate. Since it's weak, we only have partial dissociation. Partial dissociation or partial ionization or partial hydrolysis. I could do the same like they did. I could do a hydrolysis reaction, water. And therefore, if I have a beaker that's labeled acetic acid, AQ, what am I going to find? I'm going to find mostly acetic acid molecules. This will be the major species. And the minor species is a little bit of the ions that were dissociated. So the molecules and then some ions. These will be the minor species here. You don't get much. And so we can see that here in this next slide. Next slide. Over here we have hydrochloric acid. Hydrochloric acid. Well, I don't know why it's blue. But it's hydrochloric acid. Hydrochloric acid, you see hydronium ions here, H3O plus, the hydronium ions, and you see chloride ions here. For the hydronium, you have the water ends of the water molecule. I mean, the oxygen ends of the water molecule. For the chlorides, you have the hydrogen ends of the water molecule. Over here, we have acetic acid. Acetic acid, we have mostly molecules of acetic acid that have not dissociated, and then a few dissociated ones. Here's one acetate, here's one hydronium. That's what we have there. When I write H plus here, you know, I'm thinking hydronium. Because that H plus is going to react immediately with water to form hydronium, but I'm not going to show it. Here are some numbers for that. You know, strong acids like hydrochloric acid are almost completely ionized here, 99+%. But the percent ionization varies depending on concentration. So here it goes closer to 80% ionized. Whereas hydrofluoric acid is a weak acid. And you can see the percent ionization is much smaller. It's 22% ionized. That means it's 78% molecules. At 0.1 molar, it's about more than 90% molecules. And so the major species in hydrofluoric acid would be HF molecules. The major species in hydrochloric acid would be the ions. So that's showing the major species. Major species in HCl, major species in HF. Okay. Minor species would be HCl molecules, but very few. Let's see. And the minor species in HF would be the ions. All right, now we're going to go to bases. Bases hydrolyze. All bases hydrolyze. So I have no choice. For the acids, I'm lazy, so I'd like to ionize them rather than hydrolyze them. This is left writing. For bases, I can't. I have to hydrolyze. I have to hydrolyze. So let's take a look at strong base. Strong base like sodium hydroxide. Sodium hydroxide is solid. So the first thing is I ask myself, is it soluble? Is it soluble? Yes, it's soluble. It's soluble, and therefore dissolves in water, so I get sodium hydroxide AQ. And then I ask myself, is it a strong, weak, or non-electrolyte? At this point, I call this a soluble salt. It's a soluble salt. Soluble salts are strong electrolytes, so they're going to ionize into ions. And then I have my hydroxide. My hydroxide, this is the strong base. Now, what the strong bases do is they don't ionize. The strong bases hydrolyze. So I'll take my strong base. Strong bases are strong electrolytes. Strong bases hydrolyze completely. And so I get hydroxide and water. Hydroxide and water yields water and hydroxide. So pretty much no change there. So let's do another one. The next example I'll do is sodium sulfide, Na2S. If I do sodium sulfide, is it soluble? Sodium sulfide soluble? Yeah, all sodium salts are soluble. And so sodium sulfide dissolves in water. So we'll get Na2SAQ. And then I ask, is Na2S a strong, weak, or non-electrolyte? Well, this is a sodium salt. Sodium salts are soluble. Therefore, it's a strong electrolyte. 2 sodiums and a sulfide. And then it turns out the sulfide is a strong base. And what do strong bases do? Strong bases hydrolyze water completely. When strong bases hydrolyze water, they take a hydrogen from water. They take a hydrogen ion, an H+, and I'm left with hydroxide. So my strong base hydrolyzes water completely to form some hydroxide. Hydroxide is a strong base. Let's look at another strong base. Sodium oxide, solid. And so sodium oxide, solid, dissolves in water, yes, forms sodium oxide, AQ. Sodium oxide, AQ, is a soluble salt, so that forms 2 sodium ions and an oxide ion. Oxide ion is our strong base, and strong bases hydrolyze water completely. And so oxide reacts with water to form hydroxide plus hydroxide. In other words, water loses the hydrogen. And so strong bases hydrolyze completely. Strong bases hydrolyze completely here. I could do the same thing for amide. Do one more. If I do sodium amide, solid. Sodium amide solid is soluble. All sodium salts are soluble, so I'm going to get sodium amide AQ. Sodium amide AQ is a strong electrolyte because it's a soluble salt, so it's going to dissociate into the ions sodium plus and NH2 minus. Amide is a strong base, and strong bases hydrolyze completely. So amide reacts with the water to form, water is going to give up a hydrogen. It's going to form ammonia and hydroxide. Those are some examples of strong bases. What do all these strong bases have in common? They all end up producing the same species in water. What species is that? Hydroxide. Let's do an example of a weak base. I'm going to pick a weak base like sodium carbonate. Sodium carbonate's a weak base. Sodium carbonate's a solid. It's a sodium salt, so all sodium salts are soluble, so I can dissolve it in water to get sodium carbonate. It's a soluble salt. Soluble salts are strong electrolytes. So it forms sodium ions, 2 of those, and a carbonate ion. Carbonate is a weak base.